the Bosavar Law, and Ampere's law. Okay, magnets are caused by moving charges. Moving charges cause magnetic fields. Every magnet that exists is caused by something is moving around. Even a permanent magnet is caused by electrons spinning around atoms. And we know, like, the Bohr model of the atom doesn't really exist. Electrons don't literally spin around an atom. Electrons have what's called spin. It's a quantum mechanical intrinsic property of electrons, but it has units of angular momentum. It is like a spinning electron. And we'll talk about that a little later. But in the macroscopic world, magnetism is caused by moving charges, and it follows, the magnetic field follows the Bosavar law. That should be written here somewhere. You'll see how it's spelled in a second, which looks like this. So this says you have a moving charge. So I've got some charge Q that's moving at some velocity vector V. I want to find the magnetic field some distance r away from that charge, where it is at this particular moment. So let me write down our formula. That's our hat. So I want to find, say, the magnetic field at this point P. Then what I do is I draw a vector from my position where the charge is towards where I care about. This is the point where I want to find the magnetic field. So I draw a unit vector that points toward that. We call that r hat. Then the magnetic field at that point is a vector that's q times v cross that r hat divided by this distance here squared. So it's a cross product, and it follows the right-hand rule. So in this particular case, at that point P, the magnetic field would point in the direction of V cross R. So you point your pointer finger in the direction of V, point your middle finger in the direction of that little R hat. Wherever your thumb points, that's where the magnetic field would point. So down here at this point P, the magnetic field would point into the board. What about back here? Say some other point S, I don't know. So we would draw a little R hat there that points toward our observation point. V cross R, V cross R still points down. So the magnetic field would point down there. What about some point up here? Call it point T. Now, in order to do V cross R, see, remember the cross product is you point your fingers in the direction of the first one, curl toward the second one in the smaller direction of curling. So toward V, V toward R would be curling that way. V toward R. V cross R. I can't go like this because I'm not looking at this big angle between V and R. I'm looking at the smaller angle between V and R. V cross R, my thumb points up. So up here, the magnetic field would point out of the board. And of course, we know how to find the magnitude of a cross product. The magnitude of B would be Q, magnitude of V, magnitude of R hat, that's just 1, times sine of the angle between them over R squared. So when we say the angle between two vectors, we always mean the smaller angle. If I've got two vectors here, say V and W, I could, if I wanted to, call this the angle between them or this. Well, whenever we say the angle between two vectors, we mean the one that's less than 180, less than or equal to 180. So we mean that angle. Moving charges create magnetic fields. So just using the Bosavar law, if I've got some charge moving with velocity v, the magnetic field, here's a shortcut. All that stuff I just did is the hard way. Here's a shortcut for finding magnetic fields. Anytime something is going straight, use your thumb for the straight thing and your fingers will curl around in the curly thing. And that applies to almost everything we do this semester with right-hand rule. So somebody's going straight. This charge is in free space. Nothing is around. I've got this charge here. It's moving in a straight line. The magnetic field then, I put my thumb in the direction of the guy going straight, and the magnetic field will curl around this line in circles. So that will be into the board on this side and out of the board on this side. Okay, your book has much better pictures of that than I can draw. We're going to do this problem in a minute. I'm going to come back to that. I want to show that picture though. Okay, so here we have a current. And so instead of just one single charge, we've got an entire current of charge. We've got a bunch of charges all moving along this wire here. And we want to find the magnetic field around that wire. Well, we can see here just doing I cross R. Down here, we get magnetic field lines that point down. Up here, at this spot, we get magnetic field lines that point kind of out this direction and so forth. So the magnetic field lines spin around our current carrying wire. I've got this nice picture here somewhere that's like a... Okay, so here's some current carrying wire. Magnetic field lines spin around it. So like if we were to cut this plane right here, the magnetic field line would be coming out of the plane. Over here, the lines would be going straight down. Back here at that spot, the magnetic field is coming straight up. Magnetic field lines spin around currents. Okay, so magnets are caused by moving charges. Magnets also affect other moving charges. So let's say we had this scenario here. I've got a moving charge here. It's got velocity v. That's going to create a magnetic field everywhere in space. If I had a stationary charge sitting up here somewhere, it wouldn't care about that magnetic field. Stationary charges don't even notice magnetic fields. But what if I put another moving charge in here? This guy is going to create a magnetic field at that spot where this charge lives at the moment. Because this charge is moving, it's going to feel a magnetic force. So let's actually work out these vectors here. So FE here is the electric field. The electric field doesn't care that these guys are charged or are moving. The electric field of two positive charges tries to push them apart. So this guy here feels an electric field from him that creates an electric force that points up. He would also feel an electric force that points down, but right now we're just focused on this guy. Now, because both of these are moving, he will also feel a magnetic force. Let's figure that out. Okay, so I've got this guy's moving in this direction. I've got another charge here. I'm going to label these Q1 and Q2, call that V2, V1. Okay, so this guy's going to feel a force from the electric field and the magnetic field caused by him. We don't care about that right now. All we're worried about is what happens to this guy. So he creates a magnetic force or a magnetic field everywhere in space. Moving charges create magnetic fields. So we could do B equals QV cross R hat over R squared to figure out the direction. We're not worried about the magnitude yet. To figure out the direction of the magnetic field up here at this spot. I could play the same game to find the field here, 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 anywhere, but that's where my charge is, so that's where I want to find it. So I create a little R hat that points toward my spot that I care about. Then V cross R, V cross R, or if you prefer to use 3 fingers, V, R, B. The magnetic field will point up at that spot. So B right there, caused by V1, points up, out towards your eyeball. Or we could do that game we just did. This guy's moving in a straight line, so the magnetic field lines will go around in circles around him. So this guy creates a magnetic field that points up here, points that direction. Over here at this spot, points down into my board over here. If I go behind the plane, it will point that direction in circles around. That's the only spot I care about because that's where my charge is. Now we got to figure out what magnetic force does he feel. So we got to use F equals Q V cross B. So I want to figure out in which direction is my magnetic force. So I'm talking about the force on this guy from that magnetic field we just found. So I have to do V cross B, or V pointer finger, B straight up. The force will be that direction. So F and that will be the magnetic force. These two moving charges will repel each other. Their magnetic forces will repel each other. And of course, by Newton's third law, he'll feel the exact same force, but in the opposite direction. But we don't care about that right now. Okay, we could figure out the magnitudes, and this is kind of interesting. So let me show you. I'm not going to go through all the math. The book does it. Okay, now I left off this factor in front. Mu naught here is the permeability of free space. Remember, we've had epsilon naught all semester for electric fields. Mu naught is the magnetic equivalent of that, called the permeability of free space. It's a measure of how strongly space reacts to magnetic fields. And then, like, you don't need to know why, but we get a 4 pi in the bottom. Okay, so I was just worried about direction. So I was just writing this part down. Keep in mind, this is part of our formula. Okay. This, if we take 1 over square root of epsilon naught times mu naught, we get this number. Hey, that's c. That's the speed of light. Mu naught, by the way, is 4 pi times 10 to the negative -7th Tesla times meters per amp. It's got really weird units. The speed of light, by definition, is 1 over square root of epsilon naught mu naught. And that actually is related to, it doesn't come from that, it comes from solving the Poisson's equation for the wave equation for electromagnetic waves. We'll actually prove this later. But that's where the speed of light comes from. It's the speed at which electromagnetic waves travel. Okay, if we find Fe, we know that's KQ1, Q2 over R squared. We know FB, we know how to find that. So here's Fe. Remember, K is 1 over 4 pi epsilon naught. Here's our magnitude of B. If we take the ratio of those two, FB versus Fe, we get this. But we just said 1 over square root of epsilon naught mu naught is C. So the ratio of VB to VE turns out to be V squared over C squared, which is kind of interesting. Which means if your velocities aren't very big, C squared will be much bigger than your velocities. And the magnetic field will be very small compared to the electric field, or the forces will be very small. If V is approaching the speed of light, then this becomes significant. Okay, so that was for a single moving charge affecting another single moving charge. What if we have a whole bunch of charges? Well, then we have to integrate. So here is the Bosavar law in its most general form. B is mu naught over 4 pi. The integral of I dl cross r hat over r squared. And that's pronounced Bosavar. So we don't pronounce either of the T's. It's not Bosavar. So I here is some current that we have. Sometimes we have to turn that into a current density multiplied by some cross-sectional area. Sometimes we have to do some work with this. Sometimes that's just a single charge moving and we have to take that into account. dl, currents are not vectors, but they still point in a direction. So dl is the differential direction that your current happens to be pointing in at that moment.